Hi, this is Hermine Maas with the third installment of Univariate twin modeling with OpenMx. We've already shown in previous videos how to fit a saturated model, which will be a baseline model for various genetic models that we will explore in this video. And as you can see here, we will talk about ACE versus ADE models, which you can find details about how to fit either of these models in 1a's vc.r and 1a ADE vc.r. The 1 stands for the fact that we're still dealing with one phenotype. We're fitting either an ACE model or an ADE model. And this is a model that uses direct variance estimation for continuous data, which is what the V and the C stand for. As you'll see here, this is a path diagram for twin data where we have the monozygotic twins on the left and the dizygotic twins on the right. And we're interested in partitioning the variance in the phenotype here into sources due to genetic and environmental factors. So we have A for additive genetic factors, E for unique environmental factors, and then C and D for respectively common environmental and dominance genetic factors. Now, as you'll see in the next few slides, we don't have enough information to estimate all 4 sources of variance simultaneously, not with just data from monozygotic and dizygotic twins reared together. So we'll have to make a choice, and we'll pick either a model that includes common environment, the ACE model, or a model that includes dominant genetic factors, the ADE model, and we'll fit them alternatively. And I'll explain in a minute why we can't fit them at the same time. Remember that when we deal with twin data, we really only have 3 unique observed statistics, and those are the variance. Remember that one of the assumptions is the variance is equal for twin 1 and twin 2, as well as for MZs and DZs, so the variance only provides 1 unique observed statistic. But we have 2 additional statistics. One is the covariance in MZ twins, and the other is the covariance in DZ twins. Now, if we go back and use the rules of path analysis, we can work out what the expectations are for each of these observed statistics in terms of the parameters of the model that we're interested in. And so we're interested in the first instance, in fitting an ACE model, a model where we estimate how much of the variance is accounted for by additive genetic factors, shared environmental factors, and unique environmental factors. So then we know that the total variance is the sum of those 3 variance components. And we also know from genetic theory that twins share all their genetic variance, so VA, where this is monozygotic twins, where dizygotic twins only share half their genetic variance, so 0.5 times VA. Now, we assume as part of the equal environments assumption that the shared environment is the same for both MZs and DZs, and they're basically a perfect match for one another, which is where the information comes from to uniquely identify these sources of variance. So how do we go from the 3 unique observed statistics to then estimating the 3 unknown parameters, VA, VC, and VE? First of all, if we take the difference between the total variance and the covariance between MZs, we get a direct estimate of the unique environmental variance, VE. We can further take the difference between the MZ and the DZ covariance, which gives us a half VA. So if we square that difference between the MZ and the DZ covariance, that gives us the estimate of VA. So once we have VA and VE, we can of course work out VC by subtraction from the total variance, or alternatively, we can calculate VC as minus the covariance of MZs plus 2 times the covariance of DZs. And you can, I think, figure out using some basic math how that is obtained. Now, it is possible, if you estimate the variances directly, that you might end up with a negative VC variance, which has to do with the relative magnitude of the MZ and the DZ correlation, which I'll explain in just a minute. It turns out that the shared environmental component and the dominance component can't be estimated simultaneously because they have competing expectations. If the MZ correlation, or maybe it's easier to put it this way, if the DZ correlation is greater than half the MZ correlation, it suggests that there is additional environmental factors that contribute to both the MZ and the DZ covariance. However, alternatively, if the DZ correlation is less than half the MZ correlation, then that might be more consistent with dominance genetic factors. And so it turns out that once you've estimated the C component, you can basically derive what the dominance component would be in case the C component, the VC component, is negative. And so dominance here can be estimated as minus twice the shared environmental variance component. And then we can also estimate or calculate what the corresponding VA would be under an ADE model. Conversely, if we started with estimating an ADE model, of course, we still have only 3 unique statistics. And the only difference here is that the expectation for the covariances in DZ twins is a quarter of the dominance variance is only shared for DZ twins compared to the complete dominance variance as MZ twins share all their genetic variants. And so if we go to similar derivations as we did in the case for the ACE model, you see that you get an estimate of VA as minus the covariance of MZ twins minus 4 times the covariance of DZ twins. Similarly, if you end up with a negative VD, you can just use a simple formula to recalculate it as an ACE model. And maybe this will all become a little bit clearer when we look at this figure that shows a range of possible correlations for the MZs, the DZs, and UN for unrelated individuals. And let's start in the middle with the forward graph. That is showing an MZ correlation of 1, a DZ correlation of 0.5, and an unrelated correlation of 0. So that pattern of correlations, with the MZ correlation being twice as high as the DZ correlation, is perfectly consistent with the variation being completely being due to additive genetic factors in red. Now, if we go to the next figure, where now the MZ correlation has been reduced from 1 to 0.8, but the DZ correlation is still exactly half that of the MZ correlation. That still means that the majority of the variance here is consistent with additive genetic factors, but that the difference between the MZ correlation and the total variance, or in this case, the MZ correlation in 1, gives us an estimate of the E component, the unique environment that makes even MZ twins differ from one another. So the third graph is just an extension of that, where we still have a 2-to-1 ratio, now 0.6 versus 0.3 for MZs and DZs respectively. But because the lower MZ correlation, we have a higher estimate of the component due to the unique environment. So any situation where the MZ correlation is about twice the DZ correlation suggests that it's only really additive genetic factors, plus maybe some unique environment depending on the how high the MZ correlation is. Now let's move to the right, where we now have a situation where we kept the MZ correlation at 0.6, but the DZ correlation is no longer half the MZ correlation, but at 0.45 is greater than half the MZ correlation. So we can still draw a line between the MZ and the DZ correlation, and it cuts at about 0.3. And that is really suggesting in this case that of this familial variance that is different from, that makes people in a family more similar, half of it is due to additive genetic factors and half to shared environment. So you'll see a couple more scenarios where the DZ correlation is greater than half the MZ correlation. And in the second one from the right, the DZ correlation is now 0.5, with an MZ correlation of 0.6. So suggesting that more of the variance is now due to shared environment, as both the MZ and the DZ correlation seem to be bumped up to the same extent. But there is still a little bit of evidence for additive genes because the DZ correlation is still less than the MZ correlation. In the final graph on the right, the MZ and DZ correlation are estimated to be the same, which is consistent with there being just common or shared environmental factors contributing to the familial resemblance, and no evidence at all for genetic factors because there is no difference between the MZ and the DZ correlation. Now let's move to the left, where where we still kept the MZ correlation at 0.6, but now the DZ correlation is 0.25, so less than half the MZ correlation. If we continue to draw that regression line, you see it cuts at about minus 0.01. And this is where that conversion from C to D comes in, because it turns out that a minus 0.1, if we multiply that by 2 and take the reverse of it, it gives us actually an estimate of the dominance variance. So that would be 20% of the variance accounted for by dominance genetic factors, where the remainder is still due to additive genetic factors. With the next two graphs moving further to the left, you see that first of all, the DZ correlation keeps dropping. So in the second graph, it's now at 0.2 compared to an MZ correlation of 0.6. So suggesting that there is a greater proportion of that familial variance now due to dominance compared to additive genetic factors. And then at the extreme where the DZ correlation is about a quarter of the MZ correlation, that would be consistent with the whole genetic variance being due to dominance genetic factors. Now, this may not be biologically very plausible. It's unlikely to have an interaction between alleles without having a main effect, but it's not impossible to observe correlations of that nature. So you see here that if you fit an ADE model, you could end up recalculating it as an ACE model and vice versa just by using those conversion formulae. So I hope this gives you a better sense of how we go from twin correlations to estimating sources of variance. So for the actual data that we have in this example, BMI, we notice that there is, just by plotting the values for twin 1 versus twin 2 in MZs and separately in DZs, that the MZ correlation is about 0.78 and the DZ correlation about 0.30. Thus, the DZ correlation is less than half the MZ correlation, which is consistent with potentially being additive and dominance genetic factors contributing to this phenotype rather than shared environment. So what we'll do now is go through the OpenMx script that fits the ADE model, but it's easily adjusted to fit the ACE model, and we'll estimate the contributions of genetic and environmental effects on the total variance of this phenotype. So here are the two path diagrams for doing this type of modeling, and we're focusing here on direct variance estimation, because it has a number of desirable statistical properties that we'll go into in a bit. So if we take this down and translate this path diagram into OpenMx code, we are now going to use 3 different MX matrix statements to each capture one of the 3 possible variance components. So we have Cov-A, which is the object that will estimate the parameter for the additive genetic variance. And so this is a simple 1-by-1 matrix that is free, and that we give a start value and also a label. Note that the label and the name of the matrix has to be different. So we tend to add the number of rows and columns, or the specific number of rows and columns to the label. Notice in this case also that we've used a different name within the matrix as outside for the object that holds the matrix. And you'll see in a minute how that gets used later on in the script. And so similarly to the Cov-A object, we have a Cov-D and a Cov-E object containing in each case the variance component for each of the 3 ones that we want to include in the model. Now we also know what the expectation is for the total variance. It's basically just the sum of the 3 variance components, and we can generate this by using an MX algebra statement, which can take an expression and a name as its arguments. So the expression here is basically just whatever algebra we want to do on the matrices that we've already defined. And note that here we use the names used within the MX matrix statements, the VA, VD, and VE names, rather than the Cov-A, Cov-D, and Cov-E names. The sum of these 3 components will be stored in a matrix called V, contained in the object Cov-P, the covariance of the phenotype. Now, we also know from genetic theory what the expectation is for the covariance of MZ and DZ twins, and so we can similarly use MX algebras to work out those expectations. So VA plus VD for the MZ covariance, and because each of these matrices are 1-by-1 matrices, the sum of them is also going to be a 1-by-1 matrix. And then finally, for the DZ covariance matrix, we have to multiply the additive genetic component VA by 1/2 and the dominance component by 1/4, 0.25. Now that gives us the individual variance components, but what we really need to do is come up with the expectation for the covariance matrices for MZs and DZs, in addition to those of the means. The means we already know how to do, and we're just going to reuse a full 1-by-2 matrix here, but because we've tested the assumptions and we know that the means can be equated, we're going to actually use the same label for the mean of twin 1 and twin 2 and use this across the 2 groups for both the MZ and the DZ group, because the means could also be equated across the 2 groups. Now let's go back to the expected covariance matrices. Those are going to be of the order of 2-by-2. Where on the diagonal, we have the variances, and on the off-diagonal element, the covariances. So to generate this algebra that creates a 2-by-2 matrix, we're going to use an R-bind and a C-bind command. And these are OpenMx specific operators that allow us to concatenate matrices. So R-bind will concatenate 2 matrices that have the same number of rows, then C-bind will concatenate matrices that have the same number of columns. And I might have just reversed this right now. But basically, so we have C-bind concatenates the top row here. So they have the same number of rows. And then we have a second C-bind for the bottom row. And then we stick those 2 together in an R-bind. I hope that makes more sense now. Thank you. So if we then look at what this looks like in the script, you see we have one mean G matrix that you'll see we'll reuse for both the MC and the DZ groups. We have the three matrices for the variance components, and then we have all the algebras to generate the expected variance, the expected covariance, and then use R binds and C binds to put them together in 2x2 expected covariance matrices. Now here you see the rest of the script, and you might start to recognize some of this. The data statement is exactly the same because we're fitting just a new model to the same data as before. The expectation objects are also looking very similar, except now that we use the new generated expected covariance matrices separately for MZs and DZs, but use the same mean G matrix for both the MZs and the DZs. Then we need to pull all these objects together into an MX model for MZs and for DZs that we then evaluate together using the MX fit function multigroup. But before we do that, you may notice that some of these objects that we are needing for the MZ and the DZ group now, the additive genetic variance, the dominance variance, the unique environmental variance, we need those in both groups. And rather than having to type them in twice, we put those elements that are common to both groups into a list that we call parse for parameters. You can call it whatever you like. And we stick that in both model MZ and model DZ so that it automatically includes both or all 5 of those objects into the 2 groups. The only other thing that's kind of different here is that we added a little bit of extra algebra here to generate basically another matrix that calculates some of the standardized variance components. We don't have to do it as part of the script. We could do it afterwards, but by having it in the script, it's automatically done and it doesn't really take that much time in a simple model like this one. So we also provide that little matrix, some column labels and some row labels to make it more readable. And so what we stick here together is the 3 variance components, VA, VD, and VE, as well as how much of the variance each of those variance components contributes to by dividing each of them by the total variance. And we call this new matrix US as the unstandardized and the standardized variance components that we might want to inspect after we fit the model. We can also estimate confidence intervals, and in this case, not just around the means or the variances or the covariances, but around either the unstandardized or the standardized variance components. So we can just have a list of elements to calculate the confidence intervals for. And we stick all these different objects in our new model, which we now call model ADE, that we can then run with an MX run command. Notice here that in this case, we do want to estimate the intervals. And so that needs to be indicated as well as part of the MX run function. Now we will want to compare this model with the saturated model to see how well it fits the data. But rather than having to refit the saturated model, if we started this in a new session, for example, we could just use the fit statistics, the -twice log likelihood and the degrees of freedom from this saturated model and use another function that we have in our myfunctions.r script to generate the likelihood ratio test and its corresponding p-value. We can also still use our fit GOFs and fit EST functions to print the goodness of fit statistics and the parameter estimates, but note that we also want to maybe print the confidence intervals. So we have an additional function here that prints not only the estimates, but also the confidence intervals. Now, there's a variety of ways to do all these things. And so this is just one way that we've chosen and that we will consistently use throughout, but you can change it whichever way you like. So Once we've figured out the script, we've run it, we can then use summary to get not only the fit statistics, but also the estimates out. So in the summary, we'll first get a table of the free parameters, followed by the confidence intervals of the ones that we requested, followed by the model statistics and the information criteria. Note that, of course, we can get the key pieces again by using those predefined functions. And you see here that fit-est-cis will give you not only a list of the 4 parameters in this case, the mean, VA, VD, and VE, as well as the confidence intervals around them. Note that we can also pull out any matrix from this fitted model object fit ADE by specifying the $ and then going down into the matrices that are included in that model, in this case, US for the unstandardized and the standardized variance components. And rather than showing all the different layers of this particular matrix, we're only actually interested here in the result. So we picked that and we rounded the estimates to 4 decimal places. So looking at the results here, you notice that of the total variance, which is about 0.7-ish, a good chunk is due to VA, a bit less to VD, and even less to VE. And if you make those, if you work out what the standardized components are, it suggests that 41% of the variance in BMI is accounted for by additive genetic factors, 37% by dominance genetic factors, and 21% by unique environmental factors. So here we've just summarized that same information in slightly more readable tables. And of course, in addition to that, we may want to ask some additional questions. It looks like we have potentially 3 sources of variance contributing to this phenotype. But are the estimates that we get, are they really significant in such a way that they are significantly different from 0? Do we need all 3 sources of variance to account appropriately for the observed patterns of covariance in the data? And so to do that, we would go a step further and test some submodels that allow us to identify and report the significant genetic and environmental contributions. Now, this is relatively simple, and you may remember from fitting the saturated model that we could just basically take a model, make a slight change to the model and refit it, and then compare it with the original model to see whether the constraint makes the model fit worse or not. And so we're using a similar approach here to estimate whether any of those 3 variance components significantly contributes to the variance of BMI. We might just drop them from the model and see whether the model fits significantly worse to determine whether the source of variance is significant. Now, given the E component also includes measurement error, we would never drop the E component from the model because it's pretty much impossible to measure anything without any error. And so there's always going to be some residual variance. But we could say test whether or not the dominance component is indeed significant. And in this case, we would typically not just drop the additive component, but leave the dominance component because there is no good biological explanation for that. So we end up with 2 submodels, one that drops dominance from the model, and then one that goes a step further and also drops the additive genetic component in addition to the dominance component, and thus really provides us an E model, which is sort of the baseline, the model that the lowest model that you could fit with respect to genetic models to see whether or not the genetic component to combined effects of additive and dominance genetic variance are significant for this phenotype of interest. So we do this again by using the OpenMx set parameters code, where we take the original label and instead of now constraining it to another element by using a new label, what we want to do instead here is dropping it. And that basically means fixing it, but fixing it to 0 so that it does not contribute to the variance anymore. So first we do that for the dominance component, and next we do that for the additive genetic component. And then we can use the MX compare to compare our ADE model to the AE model to the E model. And the results are going to be shown in the next table. So really what we do here, we consider now the ADE model as our best fitting model. And we're testing the significance of dominance by comparing an AE model to an ADE model. And next, we're testing the significance of A or any genetic factors by comparing the E model to the AE model. If we compare the E model to the ADE model, we test the simultaneous significance of A and D. And here are the results, the goodness of fit statistics for these subsequent models. And you see that, first of all, when we compare the ADE model to the saturated model, we have a non-significant p-value. So it means that this ADE model is a decent representation of the data given the model. But once we drop the dominance components, you see that now we compare the AE to the ADE model, and we obtain a chi-square of 4.21, which is in the diff minus 2LL column, for 1 degree of freedom, because we've dropped just one parameter, the dominance component, from the model, and end up with a p-value of 0.04, significant in this case, meaning that dropping dominance from the model makes the model fit significantly worse, suggesting that dominance genetic variance contributes significantly to the variance in BMI. Because under the null hypothesis, this test is distributed as a chi-square with 1 degree of freedom. When we go on, also drop the additive component from the model, and we now have a 2 degree of freedom test compared to the ADE model, we see that the chi-square changes dramatically. It goes up by 528, giving us a p-value of 0, basically saying there is plenty of evidence in these data that genetic factors do contribute to the variance of body mass index. So we can also, of course, we can look at this in terms of the unstandardized variance components, and we can estimate the confidence intervals, and they basically give us similar information, and they should, although in certain cases where there isn't enough power to really discriminate well between models, that sometimes you see slight variations. But in this case, what you notice is that the confidence intervals, both for the VA and the VD component, are 0.02 or 0.01, suggesting that both sources of variance are significant. So in conclusion, we have for BMI in young Australian females, evidence for additive genetic factors that are highly significant, dominance factors that are borderline significant, specific environmental factors that are also significant or that we can't drop from the model, but shared environmental factors that are not significant. And with that, we have fitted our first genetic model. So thank you very much. I provided here some basic publications that might provide a nice background to these types of models. And also one quick way to see how you can add calculations after the script has been run rather than as part of the script to save a little bit of computer time. And this is done just basically to estimate correlations. Again, this is the end of this presentation. Thank you.